Hello, my name is Lukas Landgraf, and today I'm presenting memory-efficient query pipeline processing. The traditional view on query execution plans consists of QEPs which are found through enumeration. Those usually comprise all sorts of operators, no matter how good the efficiency of those is. The state-of-the-art view on query execution is the pipeline view of query execution plans with pipeline breakers. Build sides are built on the build side of each individual hash join and result in pipeline breakers. Most pipeline breakers are subsequently used, for instance, for probing into hash tables by probing pipelines. Now let's go for an example. We have a pipeline view of this particular query execution plan with 5 base tables and 4 joins. So for this setup, we have 5 individual pipelines. The execution of these pipelines is usually comprised of executing one pipeline at a time with all available threads trying to process one pipeline. Due to interdependencies, there are 6 possible pipeline execution orders here. The first one being TSVUR, VUTSR, VTUSR, TVSUR, TVUSR, and VTSUR. In those individual diagrams, you can see the pipeline breaker lifetimes of the individual pipelines over time. The y-axis represents the memory. And as you can already see here, even though it's not to scale, the gray areas for the different pipeline execution orders are different, which corresponds to changing average memory consumption. Now let's look at the pipeline execution orders which are displayed here. Most different pipeline execution orders, as said, have different areas in the gray area. Now put to scale and project it down into a memory profile, we can see that the area below the memory profile is different. And if we now look at the difference of the area below the memory peak, called the memory integral in our case, we can see that there is a significant difference, which corresponds to, in this case, having a meaningful difference of 6.8%. Now let's look at pipeline execution orders and at the resource charts that we just looked at in detail. Each pipeline PI has a pipeline breaker VI, and each pipeline also has an execution cost EI, while each individual pipeline breaker BI also has a memory cost M. The main execution phase of the pipeline usually corresponds to the constructing phase, which we call it, in this case, of the pipeline breaker. Each construction phase is only associated with the individual pipeline's execution costs, and then after constructing, the pipeline breaker of the individual pipeline is waiting to be used by subsequent pipelines. If the pipeline breaker is not immediately used, we call this the waiting phase. When the pipeline is used, its lifetime phase is called the consuming phase, and after consuming the pipeline, its breaker is immediately allocated. As we can see here, we chose to build a bigger pipeline breaker PI before continuing to build a smaller pipeline breaker PI plus 1. The more sensible order would be to actually execute BI plus 1 first, since it has a smaller memory footprint and therefore reducing the average memory consumption through reducing the memory integral. This is our optimization space. However, we need to go into search to actually find the best possible pipeline execution with regards to memory integral. The memory profile as itself is the sum again of all active pipeline breakers, represented by the gray area here, and the area under the profile is the memory integral, which is also shown here. So let's look into the optimization space for the given example. If we now look at a particular subtree, in this example being ST, we call the subtree SI with CI in this example. This pipeline has a pipeline breaker, and the pipeline breaker BI has a tuple size WI and the cardinality FI. It can also have individual subtrees bj and pj, and the entire subtree si has an cost model cost ci, which are traditional cost model functions, for instance cout. The pipeline breaker bi also has a memory size which corresponds to the cardinality and the tuple width, and also a lifetime li. The pipeline pi itself also has execution costs, and those are calculated through taking the cost model cost ci into account and also adding writing factor sigma I. The execution cost ci then are calculated as follows. We take the cost model cost ci from a generic cost model function and subtract the cost model cost of the individual build sites on which the pipeline depends on. We also then add the writing costs. The memory costs are calculated as follows through a simple multiplication of cardinality and tuple size. Breaker lifetimes li are calculated through taking the dependencies into account and summing up the execution times during which the individual pipeline breakers is active. We also have a PEO, which is a valid PEO, meaning that all the dependencies between the individual pipelines are adhered. The final memory integral of a PEO is then calculated through summing up all the individual memory costs with the pipeline breaker lifetimes. Now, since we now have the cost, we need to transform our pipeline execution model into a task graph, since we want to know how to properly process the individual tasks by adhering the dependencies between the individual pipelines. As you can see here, we have pipeline R depend on S, we have S depend on T, we have R also depend on U, and also U depend on V, meaning that U cannot be processed before V has been processed, cannot be processed before T has not been processed, and R accordingly. We now transform this into an activity on node tree corresponding to the activity on node graph from scheduling theory literature, and annotate the nodes with the memory costs and the execution costs. Each node in it can only be processed if all predecessor nodes have been processed, and we calculate the memory integral during traversal of the graph through keeping track of the currently active nodes and their memory costs, summing them up and calling this the memory peak. Each node is active if it has been processed and contributes to the memory peak as long as its direct successor has not been yet processed. Now let's go into a more complex example. We try to transform this particular tree into a task graph, and this tree has a right deep structure RSTU and a left deep structure BCD. The right deep structure RSTU corresponds to the nodes 4, 3, 2, and 1, which are a long chain of subsequent task nodes. The left deep structure translates to a structure of nodes with a high fan-in. For instance, in this particular example, 6 has been fan-in of 2 and is depending on 8 and 7. We have 4 different search algorithms. The details of those you can find in the paper. We have exhaustive search, which enumerates all possible PEOs, returns the worst, so the global maximum in memory integral, and the best and global minimum possible PEO, and it's recursive. We also have branch pruning search, which is basically the same as exhaustive search, and it includes a branch pruning step. So returning no PEOs when a certain threshold in memory integral is exceeded. It enumerates all possible PEOs below a certain heuristic threshold, returns the best possible PEO, so the global minimum, and is recursive. We also have one pure heuristic which considers only one PEO, returns the memory integral of a PEO it finds, and relies on subsequent execution of pipeline chains in the AON tree. The theta skip search is an iteration of next possible nodes only for nodes bigger than a certain memory threshold. And for the other nodes, we don't go into recursion and log them immediately into the PEO as soon as we find them. It returns the local minimum and is recursive. Exhaustive search and branch pruning search find the best possible PEO, so the global minimum, for the memory integral, and the both and we have two heuristics. Branch binning search and theta skip search rely on reducing branching complexity by not going into recursion for certain conditions. Note that ES, PPS, and TSS share the same recursion mechanism, and TSS also includes a branch pooling step. Now to our evaluation. Our system is the pipeline execution engine prototype, which was also used, which was created as a finalist for Sigma 2018, and it relies on single-threaded PEO enumeration for all algorithms. The benchmark is the join order benchmark. The query plans are stripped of non-join operators since our prototype does not provide those operators and has four kinds of datasets. The unmodified JOB dataset, the SF2 dataset with indicated properties, the SA4 dataset, and the ICANN name SF4 and company name SF4 dataset, which is scaled accordingly. The considered queries are 1 to 13, 20, 26, 27, 30, and 33. Other queries could not be considered since it would have exceeded the available minimum memory on our system due to the pruning of non-join operators. The branch pruning heuristic would be the longest path heuristic, and the theta skip threshold is set to 1 kilobyte. We ignore final breakers since they are of constant size. For the PEO enumeration, our cost model parameters are for CI that we have cout as our cost function for the individual subtree, and the writing costs are 0 since cout already considers writing costs. The setup considers query 6. The setup for memory integral optimization potential considers query 6, 8, and 9 of the join order benchmark. The memory integral of the worst PEO is taken as the maximum in our diagrams here. The datasets are the unmodified dataset, the SF2, and the SF4 dataset. As you can see here, we got an improvement from worst to best for the indicated queries of at least 2.2%, and the maximum for query 9 was 11.1%. For the other queries, we were also able to observe memory integral improvements of less than 2%, so those are not shown here. This shows that we can actively find examples where it makes a difference to actually pick the individual pipeline execution order. For query 9, you can also see for the individual datasets the Gantt charts between the worst and the best PEO and the memory integral difference when using the corresponding peak graphs. The impact on performance considers query 6, 8, 9, 20, 26, and 33 of the join order benchmark and evaluates the enumeration durations of the individual algorithms. Exhaustive search also returns the best and the worst possible PEO. Except for query 33, we were able to observe enumeration durations of double-digit microseconds to double-digit milliseconds domain. For query 33, which is an outlier, we were able to observe an enumeration duration of 302 milliseconds due to the complexity of the enumeration on the corresponding pipeline view structure. Regarding performance stability, we consider query 6, 8, and 9 of the join order benchmark. Exhaustive search returns the best and the worst possible PEO, and datasets are unmodified SF2 and SF4 dataset. For each of the individual queries, the average of all for all possible pipeline execution orders is taken as the baseline, and the relative runtimes for each the individual pipeline execution orders is taken as the percentage of the average runtime. As we can see here, except for query 8, we were able to observe no meaningful and systematic difference between the individual runtimes for the PEOs found by the individual algorithms. For query 8, the enumeration duration was that high that it led to a higher jitter in the overall query execution time, which also considers our search algorithms. Conclusion: we contributed a development of a cost model to identify PEO based on web memory integral. We created a formal model to create algorithms to find PEOs and provide algorithms to find optimal and near-optimal PEOs. We showed that queries exist which can have substantially lower memory integral than the worst case, and showed that there is a negligible enumeration overhead. We showed that the performance of queries does not depend on a particular PEO.